So this lesson is on one more topic from math class that we're going to use a lot in physics, and that is graphing. Now, there are some of the things we're going to talk about today that you will probably remember doing in math class, in which case this sort of serves as a review and letting you know that these topics will be important in physics as well. And there's some things we're going to do here that maybe you're not used to doing in math class, but that will be required in physics. So let's jump in. Through a number of labs we're going to do in this course, you're going to be asked to do graphs from time to time. And so there's a few rules I want to go through that I sort of expect my students to do every single time they do a graph for a lab in our class. So you can think of this as sort of like a checklist to go through every time you have a lab that you're working on a graph for. So one of the first things I want you to always make sure you've done is to label the axes on your graph. You've got an x-axis and a y-axis. Generally, what we call the independent variable goes on the x-axis and the dependent variable goes on the y-axis. As a reminder, the independent variable is generally the one that you have control over. It's the one that you are sort of intentionally changing, and the dependent variable is the one that depends on this. So you generally make a change to this, or you decide what happens to this, and then this variable will change as a result of that. And it's this change that you're often trying to measure. That goes on the y-axis. Now, one thing that is common, that's necessary in physics, but maybe that you aren't used to doing on your graphs in math class, is stating the units. In math, we're often satisfied just working with pure numbers for the sake of it, but in physics, every number we work with has units, and it's important to be aware of those. You also are going to want to give the graph an appropriate title. And when it comes to actually plotting values, plotting points on your graph, a scale is going to be important. This is where you decide how much each square on your graph paper is worth. Is each square worth 1? Is each square worth 2? And a couple things I want you to keep in mind when deciding on a scale are these. So your goal should be with your scale to use the whole page, or at least close to it. But you also want to choose a scale that's easy to work with. So by that, I mean you want to choose numbers like 1, 2, 5, 10, sometimes 4. So if each square on your graph paper is worth 1 or 2 or 5 or 10, that tends to work well. Setting it so that each square on your graph paper is worth 7.9 is not going to be very easy to work with, even though it might mean you take up the whole page. So sometimes it's a bit of a balance between these two things. Once you've got your data drawn on your graph, oftentimes you'll do a line of best fit. So in this course especially, we often end up with data points that look like they lie more or less along a line. And when that's the case, doing a line of best fit is a really good next step. And when you're drawing your line of best fit, you're definitely not going to freehand it. You are going to use a ruler. So let's use an example to try and illustrate and practice some of these steps we've gone over. I've kind of put together the start of a graph here. I've got a piece of graph paper. I've chosen a scale for my y-axis and my x-axis. I've plotted some points, and I've done a line of best fit. It's not completely completed though, so we got to go in and fill out a few things. One of the first things we talked about was labeling the axes. So let's do that. Now I haven't really told you what this experiment's about or where I got this data from, so we can be a bit creative here. For the purposes of this lesson, let's say I ran an experiment in my physics class where I tried some different assessment practices and to see if that would affect how popular I was as a teacher. So maybe I changed my assessment practices by varying the number of quizzes I gave to my kids in the first semester. And I measured how popular I was by the number of gifts I got going into Christmas break. So again, in most experiments, we've got two variables. One's the independent variable and one's the dependent one. The independent one is the one I have control over, that I can choose how it changes. And the dependent one is the one that probably changes, but I don't decide how it's going to change. I see how it changes in response to my independent variable. In other words, the dependent variable depends on what happens to the independent variable. So in the example I gave, the thing that I have direct control over, that I decide how much it changes by, is the number of quizzes I give my students, is my assessment. So we'll put that down here on the x-axis where the independent variable should go. And then I was going to see how that change in assessment practice affected my popularity. So popularity is going to be the dependent variable. I don't directly decide my popularity, but I see how it changes depending on my assessment. Okay, and remember, in science class, units are really important. So I'm going to measure my assessment by the number of quizzes I give. That's the units I'm using for assessment, number of quizzes. And I'm going to assess my popularity using units of gifts, the number of gifts I receive. So this is the thing I'm measuring. That's the units I'm going to use. Here's the thing I'm measuring, and that's the units I'm going to use. Okay, now as I said, we want to give this graph an appropriate title. So let's call it classroom assessment. Okay, so now I've got a title. I've labeled my x and y axes, including units. I've decided on a scale for my y and my x axes. I decided to use a scale where each square was worth 1 for the y-axis and each square was worth 2 for the x-axis. Remember I said that when you're doing your scale, using numbers like 1, 2, 5, 10, sometimes 4 work out really well. Now, a couple things I want you to notice about this line of best fit. It actually goes directly through very few points. It like kind of skims that one and that one. Maybe it goes directly through this one, but even that, not quite exactly. It kind of misses almost every point. That is okay. Your line of best fit does not have to hit any point. The idea is not to hit points directly. The idea is to be as close as possible to as many points as possible. And I think this line of best fit does that. A lot of people also think their line of best fit has to go through the origin, so they force it to go through the origin. Note that the origin, 0, 0, is not even one of our data points. So that means there's no real reason for the line to go through it. We might have a data point up here. And even if this was a data point, remember the line of best fit doesn't need to go through certain data points. It just needs to be close to as many as possible. Okay, so once we have this line of best fit, we're going to look at finding the slope and the y-intercept of it. So to find the slope, we're going to choose 2 points that are on the line, not your original data points. So don't go in here and be like, oh, I'm going to choose this point and this point for finding my slope. That won't give you the slope of the line because those points aren't on your line. I often tell folks, once you've got your line of best fit, in your brain, kind of pretend that you've erased your original data points because we often don't want to look at them that much after we have this line of best fit. So here's a point on the line of best fit right there. Now that's not a great point to use because it's hard to figure out what the coordinates are of it. It's maybe 15, 16, 17, 18 and a half on the y-axis, and on the x-axis it's, let's say 12.3 or something like that. Hard to figure out exactly what that point is. So we should try and pick points that are on the line but that are easy to measure or easy to read. For example, this point up here to me looks very easy to read. That line goes pretty much directly through that crosshairs up there on the grid, so it should be quite easy to get the coordinates. And I want to pick another point. I think right down here is going to be pretty easy to read as well. Again, the line seems to go right through the crosshairs. And the good thing about these points is I've chosen them to be as far apart as possible. That's important when you're choosing points to find your slope. So now let's calculate slope. Remember the formula for slope is rise over run. So if we want to get a number for our slope, we're going to plug in numbers for the rise and for the run. Now, quick reminder, the idea with rise and run is to get from my first point to my second point, I need to rise up a certain amount along the y-axis. And then I need to move horizontally a certain amount. I need to run a certain amount parallel to the x-axis. So that's what I'm talking about when I use the words rise and run. We can count out what the rise and the run are, but first it might be useful to actually know what these coordinates are for the 2 points I've selected. This point looks like it's got an x-coordinate of 6 and a y-coordinate of 9. My second point seems to have an x-coordinate of 20 and a y-coordinate of 29. So in my rise, I'm going from a height of 9 to a height of 29. So my rise is 20. On my run, I'm going from this point at 6 all the way over to this point at 20. So to go from 6 to 20 means my run is 14. One really common mistake that students make is they measure their rise and run just by counting squares. So they might look at this run and say this is 1, 2, 3, 4, 5, 6, 7 squares, so my run is 7. We're not counting squares here. We want to use our actual units. So we want our run to be in numbers of quizzes, not squares. And that means I have to use the scale I gave. Since I decided on a scale where each square is worth 2, I need to apply that scale here. So 7 squares means a run of 14. Easiest way to do it is to just read the coordinates off of the scale you've written on your axis. But use your scales, don't just count squares. So if my rise is 20 and my run is 14, then I can calculate slope by going 20 divided by 14. And I can reduce that to 10 over 7. And in math class, I would probably leave it there. But in physics class, I tend to like decimals. It's just easier. When I look at the number 10 over 7, I'm like, okay, what's that number? Is it close to 1? I think it's a bit bigger than 1. Is it close to 2? I think it's less than 2. How much less than 2? Is it closer to 1 or closer to 2? I like a decimal because I just know exactly how big it is. So if we put that as a decimal, we get 1.4. Okay. The math part is done, but again, this is a science class, so units are important. This might seem a bit weird to you to give units for a slope, but it is, like I said, it's important. So how do we do that? Well, in order to get a number for the slope, I put in a number for the rise and a number for the run. But I can use any equation, not just with numbers, but with units as well. If I want to get a unit for the slope, I should put in a unit for the rise and a unit for the run. Let's try that down here. So the units of my rise, which was along my y-axis, is going to be gifts. And the units of my run, along my x-axis, should be quizzes. So that means my slope, my rise over run, has units of gifts divided by quizzes, or gifts per quiz. So putting this all together, I can say my slope is 1.4 gifts per quiz. Okay. The nice thing here with using units with the slope is it gives me a bit of an intuitive understanding of what the slope means. 1.4 gifts per quiz. That means every time I give my class an extra quiz, I can expect an extra 1.4 gifts at Christmas time. That sounds like a pretty good return. Okay, let's also look at the y-intercept. So the y-intercept in general is the y value where the line crosses the y-axis. And so we can see that is happening right over here. Here is the point where my line crosses the y-axis. And that y value is, well, it's between 0 and 1. Let's call it about 0.5. And again, just like we needed units for my slope, we want units for the y-intercept as well. The y-intercept is a y value, so it's measured in gifts. So again, this has a bit of an intuitive understanding. The y-intercept is the popularity I would expect, based on number of gifts, if I were to give no quizzes? So looking at the upcoming semester, I see if I give no quizzes at all, I'm going to automatically get a half a gift somehow. So I'm guaranteed a half gift. That's my starting position. If I'm okay with that, maybe I don't give any quizzes. But if I want more quizzes than that, I better give some more gifts than that. Sorry, I better give some quizzes. And again, for every quiz I give, I can expect an extra 1.4 gifts. Okay, so what we've kind of been doing here, I like to think of it as simplifying the data we have. So with every step, we kind of simplify a bit further, and we also add more meaning. We started off with a bunch of points on a piece of paper. That was not very simple. There was a lot of data there, and it didn't have much meaning. We changed that to a line of best fit. That's a little more simple, and it has a little bit more meaning. It has a trend. I can see the direction it's going, etc. Then I took that line of best fit, and I reduced it to two numbers, a slope and a y-intercept. Again, that's a lot more simple. I don't need a big page to draw these out. It's just two numbers. And I've added some meaning here too. I see that the slope is the number of gifts I get per quiz I give. So with every step here, like I said, the way I think of it is we're reducing the complexity and we're adding meaning. And the final thing we want to do is take all of this information. What are we measuring on the y-axis? What are we measuring on the x-axis? What's our slope? What's our y-intercept? And put it all together in one nicely packaged form. And that we're going to do by finding the equation of the line. So you might remember from math class that the formula for the equation of a line is y equals mx plus b. M is the slope of the line and b is the y-intercept. And one thing I want you to make sure you're doing in physics class, although you might not do this in math class, is I want you to replace y and x with something different. In a math class where we're just kind of playing around with numbers and they don't necessarily always mean anything in particular, y and x are great. Y tells me it's the number on the y-axis, x tells me it's the number on the x-axis. But in our example, our y-axis and our x-axis were measuring very specific things. They were measuring popularity and assessment. So rather than using y and x, I'm going to pick new letters that tell the reader I'm talking about popularity and I'm talking about assessment. So I think I'm going to use P for popularity instead of Y, and I'm going to use A for assessment instead of X. So if I take the equation of a line, y equals mx plus b, and instead of y, I put P for popularity. Instead of m, I put my slope, 1.4. Instead of x, I put A for the assessments I give. And instead of b, I put my y-intercept of 0.5. Now I have kind of all the results of my analysis nicely packaged into one equation of a line. And this tells me exactly how much popularity I can expect, measured in number of gifts, for any amount of assessment I do, measured in number of quizzes. So if I want to know, okay, I think I can squeeze in 13 quizzes before we close for the holidays, how many presents can I expect to get? I can easily do that by plugging a number in here and solving for P, my popularity. Okay, so again, these are steps that I would like you guys to go through whenever you do a graph for me on one of our labs in this class. I would hang on to this lesson sheet. Think of it as a checklist of things you need to do when you're working on one of your labs that has a graphing component for this class. Thanks. See you in the next lesson.